Hello everyone. In this video we will be factoring quadratics when a does not equal 1 starting in standard form. Ax squared plus bx plus c. Okay, let's consider this first example. It says determine the missing factor. First factor is given to us as x plus 6, but we're going to factor fully and then we'll examine the missing factor. So let's start with our 2x squared plus 13x plus 6. And let's use the product and sum technique here, more efficient, which includes decomposition within it. And you'll see in the next few seconds where the decomposition fits in. So let's first consider factors of 2x squared. We can use 2x times x to equal 2x squared. And then factors of 6. Factors consist of 1 and 6 or 2 and 3. We're going to go with 1 and 6. 2 times 6 equals 12x. And x times 1 equals 1x. And if you add 12x plus 1x, that will equal 13x, our middle term, the bx term. And if you were to use decomposition, then 13x would decompose down to 12x plus 1x, and then you would factor by grouping and then common factoring, and you'd end up with your factors. However, we're using the product sum technique, which works its way forward into decomposition. And we found the pairs of factors, 2x times x to equal 2x squared, and 6 times 1 to equal 6. And the product of those factors, when added together, that's the sum of 12x plus 1x equals 13x. So in this technique, we can go straight into our factors. We'll put our equal symbol, we'll open up two brackets, and the first list of factors, 2x and x, gets written first inside our brackets. And the second list of factors, 6 and 1, gets written second. However, we need to be very careful because we want the 2x to multiply with 6 to equal 12x squared. And that means they have to go in separate brackets. So the plus 6 will go in this bracket, which when you expand, 2x times 6 will equal to 12x. And the plus 1 goes in the first bracket, and when that gets expanded, it becomes 1x, and the 12x plus the 1x, we've already shown, equals the sum of 13x, which is why they're the correct factors to use. So there you have it. We started in standard form, and we converted into factored form by using a factoring strategy called product and sum, where the product of these factors leads to a sum of 13x, which equals the bx term, the 13x, and allows us to write our two binomial factors, 2x plus 1 and x plus 6. And when we consider the choices above, x plus 6 is given as the first factor, so the missing factor is 2x plus 1, which is choice D. And that concludes this first example. Okay, in this second example, we will examine the quadratic relation given, and we will use it to determine the x-intercepts, the equation of the axiosymmetry, the coordinates of the vertex, and the y-intercept, which will allow us to sketch the graph of this relation. Okay, let's begin with the x-intercepts. In order to determine the x-intercepts, we need to factor this quadratic. And it's in standard form, and a is not 1. We might notice a common factor, so let's begin there. So let's divide each term by a common factor of 4. So 8x squared divided by 4 is 2x squared, and positive 12x divided by 4 is 3x. And negative 36 divided by 4 is negative 9. So we notice that the standard form still has an a value not equal to 1 inside the brackets. So we'll continue with the product and sum technique. Let's consider factors of 2x squared, 2x, and x. And let's consider factors of negative 9, 3, and negative 3. And then let's multiply these factors, and we'll get the first product of 6x. We'll multiply the next two and get a product of negative 3x. And when we add these products, we'll get a sum of 3x. So we found the combination of factors that lead to products which lead to a sum of 3x. Again, we're using the product and sum technique here. You might find this technique a little bit more efficient. It has decomposition built into it. The 3x inside the brackets gets broken up into 6x plus negative 3x. But we worked forwards with that instead of working backwards. And we could write this in factored form now. The original factor of 4 remains, brackets, 2x in the first one, x in the second one. The 2x needs to multiply with the positive 3. So that means the positive 3 goes in a different bracket, and the negative 3 goes in the first bracket. So we went from standard form to factored form. Now we could take each of these factors and set them to 0. Because we're looking for the x-intercepts, if y equals 0, we are on the x-axis, and thus the ordered pair would be an x-intercept, also named the zeros. So let's take 2x minus 3 and make that equal 0. Let's bring over the negative 3. That becomes positive, and let's divide by 2. So the first x-intercept is 1.5. And as an ordered pair, that becomes 1.5 comma 0 for y. And now let's consider the second factor, x plus 3. Let's also set y to 0 and make that equal 0. And bring over the positive 3, and it becomes negative 3. So the second x-intercept is negative 3. And let's write that as an ordered pair. Therefore, negative 3 comma 0 is the second x-intercept. And that concludes part A, determine the x-intercepts, also known as the zeros. Okay, let's continue, and let's now find the equation of the axis of symmetry. So in general, the equation for the axis of symmetry is x equals h, and h is the x-coordinate in the vertex. And if we take our x-intercepts and find the midpoint of them, so 1.5 plus negative 3, and we find the midpoint of them, so we add them and divide by 2, that'll equal negative 1.5 over 2, which equals negative 0.75. And when x equals negative 0.75, this becomes the equation of a vertical line. And the vertical line, so if we do a sketch of our parabola, the vertical line is an imaginary vertical line. It's an axis of symmetry that splits the parabola in half. And where's the parabola split in half? Where is the axis of symmetry? It's located at the vertical line called x equals negative 0.75. And thus the equation of the axis of symmetry. Okay, let's move on to part C, determine the coordinates of the vertex. Well, we could take this axis of symmetry, x equals 0.75, excuse me, and substitute it into the equation. So y equals, let's go back and get our equation, 8x squared plus 12x minus 36, 8x squared squared plus 12x minus 36. Okay, our next line will equal 8 times, and negative 0.75 squared is 0.5625, plus 12 times negative 0.75 equals negative 9, or subtract 9, minus 36. And then our next line, 8 times 0.5625 is 4.5 minus 9 minus 36, which equals negative 40.5, which is the k value or the y coordinate in the vertex. Recall your vertex is h comma k. We solved for h in the previous question where we had to find the equation of the axiosymmetry, and that's negative 0.75, which we used in part C to get the y coordinate. We subbed it into the equation and solved for y, which is the k value, or the y coordinate in the vertex, which is negative 40.5. And we have just determined the ordered pair for the vertex. Okay, and next, part D, we need to determine the y-intercept. And recall, we were given standard form, 8x squared plus 12x minus 36. So there's two ways that we can get the y-intercept. We can let x equal 0. We could sub x equals 0 into the equation and solve for y. Or we could recall our knowledge that in standard form, ax squared plus bx plus c, that in standard form, the c value is the y-intercept. And it becomes a shortcut. And notice that if you sub in 0, the first term becomes 0 squared times 8, which equals 0. And the second term becomes 12 plus 12 times 0, which equals 0, minus 36. So subbing in 0 would lead to negative 36, or recalling that the c value in standard form is the y-intercept is a shortcut to that fact of what the y-intercept is. So therefore, the y-intercept as an ordered pair is 0, negative 36. So let's look back at the original question. We needed to examine the quadratic relation to determine the x-intercepts, then to find the equation of the axiosymmetry, then to find the coordinates of the vertex, and finally to determine the y-intercept. And taking all this information together, we can sketch the graph of this relation. So let's consider all this information. And I'm just going to zoom out and zoom in on the graph that I've already sketched ahead of time. And let's open this right up. Okay, there you go. So the y-intercept of negative 36, the vertex, and the x-intercepts, which we can't see right now because we're zoomed out, are located here, negative 3 and 1.5. And we plot those 4 key points and we draw our parabola through them, and we have our sketch of this quadratic relation. And let me zoom in on the x-intercepts so we could recall those. We have our factored form, y equals 4 bracket 2x minus 3 close bracket x plus 3. That led to our first x-intercept of 1.5 and our second x-intercept of negative 3. So 1.5 comma 0 and negative 3 comma 0. And zooming back to the graph, we could see our x-intercepts, we could see over here, we could see our y-intercept, and we could see our vertex. And then our curve goes through them all. That concludes this second example. That concludes the video. Thank you for watching this video on factoring quadratics when a does not equal 1. In the first example, we factored a quadratic. In the second example, we factored to find the x-intercepts. Then we found the midpoint of the x-intercepts to determine the equation of the axiosymmetry, which is the h value, the x coordinate in the vertex. Then we sub that value back into the equation to determine the y coordinate in the vertex, which is the k value. Then we recalled standard form that c equals the y-intercept to determine the y-intercept. And then we took these four ordered pairs, x-intercepts, y-intercept, and vertex, and sketched a graph of this quadratic relation. That concludes the video. Thank you for watching. Have a great day. You guys are awesome.